Hello class, in this video we're going to be looking at naming and writing the chemical formula of ionic compounds. The learning intention of this video is for us to predict the charges of monatomic ions, to name very simple ionic compounds, and lastly to be able to actually write down the chemical formulae of ionic compounds. Now, the main reason why we need to know how to find the chemical formula of chemical substances is because that we actually need to be able to successfully write and balance chemical equations, okay? We know that a chemical equation tells you what is the chemical formula of the reactants and what is the chemical formula of the products. So that's the reason why we actually are learning about this topic. But in order for us to actually find out and predict what is the chemical formula of ionic compounds, we need to have an understanding of how do you actually name these compounds and how do you actually predict some of the actual charges. Before I actually move on, I actually want to quickly review over monatomic and polyatomic ions. In one of our earlier videos, we've said that the composition of ionic compounds are made up of ions, but these ions can be either classified as monatomic ions as well as polyatomic ions, and we said that monatomic ions are ions or charged particles that only comprises of a singular atom, as you can see on the left hand side, whereas polyatomic ions are charged particles which consist of a group of atoms together, okay? And as you can see by these three examples, or these three ionic compounds, we can see that this particular one over here contains one monatomic, and it contains a polyatomic anion. This over here contains a polyatomic cation and a polyatomic anion, and the example below over here contains one monoatomic cation and one monoatomic anion, okay? And again, this is just a review. So we said that monatomic ions are charged ions that consist of one atom, and it's important that you don't spell this as monoatomic, it's just spelled as monatomic. Now, something that I probably haven't gone through in a lot of detail in our last video was how do you actually predict what is the actual charges for these monatomic ions. So the way that we do this is we just need to identify the number of valence electrons that particular atom has, and remember that is given by the group number, so the actual column number that the element is found in. And then all we really need to do is pretty much identify how many electrons does it actually need to lose or gain so that it has a full valence shell, so that it has an electron configuration similar to a noble gas, okay? So let's look at these three examples over here. The first one being nitrogen. Nitrogen is found in group 5 over here, so that means it's got 5 valence electrons. In order for it to have a full valence shell, it needs to therefore have 8 electrons, and what it will therefore do is therefore gain 3 electrons, and by gaining an extra 3 electrons, it will therefore have a net charge of -3, okay? And just remember, when you're writing down the actual ionic notation, it's the number first followed by the charge, so therefore I've written it as N3 minus, okay? And that 3 minus is a superscript, so a power. For fluorine, fluorine is found in group 7 over here, so it's a halogen. It's got 7 valence electrons. It needs 1 extra electron for it to have a full outer shell, so therefore you'd write this as F minus, and the 1 is a default. It's kind of implied. You don't have to write down the 1 at all. And for the last one, calcium, calcium is found in group 2, so therefore it's going to be Ca2+. Now, the periodic table that I'm showing you on this particular slide is a modified periodic table, and as you can see, we don't actually see the transition metals at all. The transition metals are pretty much hidden, okay? However, we do actually encounter transition metals as these transition metals actually are or form part of certain or some ionic compounds. So we actually need to know what are the charges of these transition metals for us to later on predict the chemical formula. Now, the way that we actually predict the charge of these transition metals is a bit different from how we actually do for the main group elements. So this is why I've said over here, unlike the main group elements, the ionic charge of transition metals cannot be predicted from the periodic table. One of the reasons why this is the case is because that these transition metals over here can actually have more than one charge. So that means that it could either have a +1 charge, a +2, +3, +4, and it could range up to +7, but the most common one is going to be +2. It is due to this variable charge what makes the transition metals behave so differently compared to all the other groups of elements. It is because that transition metals have varying ionic charges, there is actually no way for you to actually predict the ionic charge of a transition metal. Instead, the problem or the question will always tell you what is the actual charge of that transition metal through Roman numerals, okay? So that's what's said on this particular dot point over here. Let's now look at some examples to show you what I mean by this. So for our very first example, this is silver. Now you're probably thinking, where is the Roman numeral in this? Now in this case over here, when there is no Roman numeral given for a transition metal, that just implies that it's going to be 1. So 1, remember, it's just the default. So in this case over here, because no Roman numeral is used, that just means it's going to be a positive 1 in this case. For our next example, copper 2, obviously as you can see here, it's going to have a valency of positive 2. And for the last one, iron 3, as you can see here, it's going to have a plus 3 charge. And again, I just want to remind you that because transition metals are classified as metal steels, they will still have a positive charge rather than a negative charge. So let's see whether you can answer these two multiple choice questions. For the first question, it reads, what is the ion formed by sulfur? Now, sulfur belongs in group 6, and because it's a non-metal, it should therefore have a negative charge, and it will need 2 extra electrons in order for it to have a full valence shell. So therefore, the correct answer is going to be B. The second question reads, what is the ion formed by zinc 2, okay? So in this case over here, it's given us the Roman numeral, so therefore it's going to be Zn2+, hence A is going to be the correct answer. Now, I would like you to actually get more practice by answering the questions found on this particular slide so that you can predict charges of monatomic ions very easily. We're now going to be looking at polyatomic ions, and as I said, polyatomic ions are pretty much ions that contain 2 or more atoms together, and what you need to be able to do is that you need to memorize the charge as well as the name for common polyatomic ions. As shown by this slide over here, there is many different types of polyatomic ions, and you don't need to know all of these. The ones that I do need you to be familiar with are these ones shown on this particular table over here. So you need to know ammonium, hydroxide, nitrate, sulfate, carbonate, phosphate, so the names of it, as well as the ionic formula shown by this particular column over here, okay? Now, as shown by this particular table, most of the common polyatomic ions that you will encounter are mainly anions, okay? And as you can see here, most of them have a negative charge with the exception of ammonia. So it should be relatively easy for you to actually memorize when you do a lot of practice with these sorts of questions. We're now going to be looking at the second part of today's lesson, which is being able to actually name ionic compounds. To name ionic compounds, there are 3 main steps that you need to undertake. The first step is you just really need to identify the name of the cation, and generally speaking, this is going to be a metal. The second step is to write the name of the anion, and again, this is typically going to be the non-metal element, and all you really need to do is pretty much put them together, and that's kind of the main steps you need to undertake. However, there are a few things that you need to take into consideration. Firstly, the suffix of a monatomic anion becomes "ide." So for instance, non-metal elements such as sulfur, oxygen, bromine, iodine, fluorine, okay? Notice how most of these ends with an "ine." So what you need to do is that you need to change the suffix, meaning the ending, to an "ide." And if you do have transition metals, then make sure that you are actually including Roman numerals in the name of it as well. So I've got 3 examples over here. So for this one over here, we can see that this is clearly going to be calcium. We don't change the name of the first cation at all. However, this is a bromine, and this is a monatomic anion. So bromine actually becomes bromide. So therefore, the correct name for this is going to be calcium bromide. This composes of a lithium. This is a sulfur atom, okay? So what you need to do is change the suffix of sulfur to an "ide." So therefore, the name of this is going to become lithium sulfide. And just to point it out that sulfur or any sulfur name or word should have a PH rather than an F. PH is for Australian spelling, F is for US, I believe. And for the very last one, this is copper, that's oxygen. Oxygen is a monatomic anion. Change oxygen to a suffix with "ide," so therefore it becomes copper 2 oxide. And again, I want to point out that it's critical for you to indicate the actual charge of the transition metal, since transition metals can have varying charges. So now we're going to be looking at some examples how you could actually name ionic compounds with polyatomic ions present in it, and it follows the exact same process, okay? So for the first one over here, just identify the cation component. That's going to be ammonium, and this over here is fluorine. Just change fluorine to a fluoride, so therefore it's going to become ammonium fluoride. This one over here is calcium. This one over here is sulfate, so therefore this is going to become calcium sulfate. You don't need to change the prefixes of this one because this is a polyatomic. You only need to change it for monoatomic anions, okay? For this one over here, this is your cation, so that's magnesium. Leave the name as it is. This over here is nitrate, so it's just going to become magnesium nitrate. And for the very last one, that's the cation. This is the anion over here, so it's going to become sodium hydroxide. What I like you to do is I want you to please use this particular table over here so that you can answer the questions on the next slide. So give yourself 5 to 10 minutes answering these questions over here and find out what is the actual name for the following ionic compounds. So for the very first one, CaCl2, the name of this is going to be calcium chloride. The next one is going to be potassium sulfide. The next one is potassium permanganate. The next one is going to be barium oxide. Next one is ammonium chloride. The next one is cesium chloride. The next one is going to be magnesium sulfate. The next one is sodium bromide. And the very last one is going to be aluminium phosphide. Okay, hopefully you guys actually did very well. Let's move on to the next part of today's lesson. The next part is going to be learning how to actually write down the chemical formula of ionic compounds. Before I show you how to actually find the chemical formula, I'm just going to quickly explain and define what it is. So the chemical formula is pretty much a way for us to actually represent any chemical substance using pretty much the actual symbol for each element present in it. And the chemical formula, as you know, tells you the type of elements present, and it tells you how many as well based on the subscripts. So the subscripts are essentially the little numbers found adjacent to the actual element itself. The reason why we use chemical formula as opposed to using words is because different countries obviously use a different language system, and to make it a lot more easier, okay, so for instance, someone from Australia versus someone from Russia, it's just a lot more easier if we use a uniform language to indicate the exact same chemical substance, and that is by using chemical formula as opposed to the name. The ionic formula can be used interchangeably to mean the chemical formula of ionic compounds, but this is probably the most important part of this particular slide over here, and it reads, the net charge of an ionic compound is 0. And this is super important, and if you have this understanding, if you did a trial and error, you can actually check to see whether your proposed formula is correct or not by checking to see whether the ratio of cations and ions results in no net charge at all. So what do I mean by this, okay? Now, obviously, I've already given you what is the chemical formula of potassium nitrate, but let's just say that that's something that you came up with yourself through a trial and error process. So if that was your guess, let's check to see whether the actual net charge is 0, and if the net charge is 0, there's a pretty good chance that your answer is going to be correct. So in this case over here, you draw 3 potassium atoms and 1 nitrogen atom. We know that the charge of potassium is going to be +1 when it forms an ion, whereas the charge of a nitrogen atom is going to have a -3 charge. And as a result of this, if you just add these charges up, a +3 plus a -3 is going to give you a net charge of 0. So therefore, this indicates that that is the correct ionic formula of potassium nitrate. Now, the way that we actually derive the chemical formula of an ionic compound can be done in 2 ways. We could do this by drawing down the Lewis dot diagram or the Bohr model to kind of represent the electron transfer processes. So that's one way, and that's something that I've already shown you previously. But another way is by using the CRISS-CROSS method. And as you can see here, this is the shortcut method, whereas this method over here is a bit more time consuming. And I will show you both methods, but eventually I will expect everyone to use this shortcut method over here because there are some cons to this, and this won't work very well for certain situations. So I'm going to show you how to use the Lewis dot diagram. I'm not going to bother showing you the Bohr diagram because remember, the Bohr diagram shows all the unnecessary inner shell electrons, and they don't really participate at all in a chemical reaction. So the first question says find the chemical formula for magnesium chloride as well as potassium sulfide. And what I've suggested down below is you want to start off by drawing each element, so one of each, and then what you do afterwards is you then add more electron donors or electron acceptors when necessary to ensure that each element has a complete outer shell. So let me show you what I mean by this. So I'm going to first draw one magnesium and one chloride, okay? And this is what the Lewis dot diagram should be. It only shows you the valence electrons. Now, in this particular case over here, magnesium needs to lose 2 valence electrons in order for it to become stable, and chlorine would like to actually gain 1. So if this magnesium over here gives up one of its electrons over here, therefore chlorine will therefore be happy or therefore be stable, but magnesium still needs to lose one extra electron. And because it needs to lose one extra electron, you're going to therefore introduce one extra electron acceptor, okay? And in this case, electron acceptors are generally non-metal, so therefore you're going to be introducing another chlorine atom. And therefore by introducing another chlorine atom, magnesium will therefore become stable and all the atoms become stable. So therefore, if you do this electron transfer process correctly, then you would see that you would need 2 chlorine atoms for one magnesium atom, and as a result, the chemical formula of magnesium chloride is going to be MgCl2. Using the next example, potassium sulfide, again, draw one of each. So I'm going to draw potassium and sulfide. Now, potassium can lose one of its valence electrons to sulfur for it to become happy, but sulfur still requires one extra electron. So therefore, you're going to be introducing another electron donor, in this case, that being potassium. So by introducing another potassium atom, now sulfur will have a full valence shell, and therefore each of these atoms will therefore be stable. So therefore the correct chemical formula of potassium sulfide will therefore become K2S. And remember, you always write the cation first, so the metal part, followed by the non-metal. So this is how you would actually find out what is the ionic formula of ionic compounds. But one of the disadvantages of using this method is that this only works well when you've got no polyatomic ions at all. So as you can see, these are all monatomic. When you've got polyatomic, meaning you've got more, a charged particle that consists of more than 2 atoms, this becomes a lot more complex, and the time taken for you to find a formula which is worth 1 mark is just not worth it. So I'm going to show you the shortcut method, which is also referred to as the CRISS-CROSS method, and I'm going to show you a number of examples so that you become familiar and efficient with this particular method. So first step reads, predict the charge of a cation. Second step says, predict the charge of an anion. And then what you want to do is you want to exchange the charges in a X-like or a crisscross-like fashion. So what happens is that the superscripts, meaning the powers, becomes the subscripts for the adjacent element. And what will happen is that this will indicate the number of atoms present in the ionic compound. So that doesn't make any sense to most people. So I'll just show you what I mean by this. So I've written down what is the ionic form of calcium as well as bromide. And what I'm going to do now is follow step 3 is crisscross. So if I exchange this, this now becomes these subscripts. So these powers becomes the numbers down below. So the subscripts for the exchanging partner. So therefore this -1 or this 1 comes down over here, and that this +2 comes over here. However, if you actually do have a +1 or a -1 charge for one of the ions, we generally don't write 1 at all because, again, this is the default and implied number. So there should not be a 1, it should just be CaBr2. In this second example, this is going to be slightly different, okay, because this one over here has a polyatomic ion. And whenever you have a polyatomic ion present, you will generally need to actually include a bracket if the superscript of the adjacent ion has a value that's not equal to 1. So I'll show you what I mean by this. So if we were to use the crisscross method of here, the adjacent or the other ion in this case is going to be aluminium. And because aluminium is giving its +3 to sulfate, which is a polyatomic, you're going to need a brackets for this one over here. So therefore, what it will look like is Al2 bracket SO4 close bracket 3, because this 3 should belong to this whole group, okay? If you didn't use that at all, then that would imply that that 3 would therefore only belong next to oxygen in this case, which is entirely incorrect. The next example of here is also a bit different from the other 2 examples I've just shown. So this one is for iron to oxide, okay? And the reason why this one's different over here is that if you exchange the actual charges over here, it therefore becomes Fe2O2. And that seems fairly reasonable. However, when you're using this method over here, you generally want to simplify. So in this case over here, because the ratios are identical, you can kind of simplify this as a 1-to-1 ratio. So it's going to be Fe0. Let's just say hypothetically what happens if this was a +4 instead. What would happen? So therefore, if you had a 4 up here, again, the same principle still apply. You just find a common factor and simplify it. Common factor being 2. So if you were to simplify it, Fe2O4, it will therefore become FeO2. I'm now going to go through the last 6 examples so that you have a better understanding of how you can actually use the CRISS-CROSS method. So for sodium sulfite, again, just find out what are the individual charges for each of the cations and anions. Once you've done that, then we're just going to be exchanging that. So therefore, if you exchange it, you would therefore need a brackets for sulfite, because sulfite is a polyatomic ion. So the answer is going to be Al2SO4, and the 3 at the end. The next one's ammonium sulfide. So again, write down what are the charges for each of them, and therefore use the CRISS-CROSS method. In this case of here, because 2 is going to be exchanged to ammonium, which is a polyatomic, you'll need to use brackets. For the next one, strontium fluoride. Strontium is Sr2+, fluoride is -1. So therefore, to the CRISS-CROSS, it becomes SrF2. The next one is aluminium nitrate. So when you CRISS-CROSS again, because 3 is being exchanged to nitrate, and nitrate is a polyatomic, you will therefore need brackets. The next one is going to be beryllium carbonate. And in this case over here, because they have identical charges, they actually cancel each other out. So it becomes BeCO3. And the very last one is going to be chromium nitride. So chromium is a transition metal, Cr2+, and nitrite N3-. CRISS-CROSS, and therefore becomes Cr3 and 2. Now what I'd like you to do now is to answer these 2 questions over here. Give yourself 2 minutes, and then we'll compare our answers together. If you guys have done this successfully, lead 2 is going to be Pb2+, oxide is 2-. Do the CRISS-CROSS, and because that these guys actually have identical charges, they pretty much cancel each other out. They're already neutral already because of the net charge of 0. So it just becomes PbO. And for the very last one, magnesium hydroxide. Magnesium is Mg2+, hydroxide is OH-. To the CRISS-CROSS, the 2+ is exchanged to hydroxide, hydroxide being a polyatomic. So therefore, you will need brackets when you actually exchange the charges over. For the very next question over here, it reads, unknown element W has 2 valence electrons, unknown element X has 7 valence electrons. Which formula shows the most likely outcome when elements W and X react? In order for you to answer this, you're going to need to actually predict what are the charges of W and X given with the information given to you. So because it's got 2 valence electrons, that means that its ion is going to be therefore +2 because it loses these 2 valence electrons, and unknown X is probably going to be a non-metal, and because it has 7 valence electrons, it will therefore gain 1 extra electron to have a full outer shell. So therefore it's going to be X to the power of -1 to the CRISS-CROSS method, and therefore the answer is going to be B in this case. Something I like to point out is that there are a few mistakes that students often make when they're doing this particular topic, when they're using the CRISS-CROSS method. So the first mistake is obviously if you do have the incorrect charges of cations and anions, that will obviously give you the incorrect answer. But the second one is probably another mistake that I often see most of the time, and it says you're exchanging the subscripts, meaning the lower numbers instead, rather than the actual powers, which are the superscripts or the charges. So I've got the example ammonium nitrate, okay? And what people often do is that they actually exchange the lower numbers over here as opposed to exchanging these charges. And as you can see, they've done that over here. And if you guys have done this, this will be the incorrect answer, whereas this over here is the correct answer. The next common mistake that I often see is when students do not actually use brackets at all when you have polyatomic ions. So for instance, aluminium and nitrate, if this 3 gets exchanged to nitrate, which is a polyatomic, you should be using brackets, but sometimes students that do not use brackets at all will therefore put a 3 next to this subscript 3 already, which implies that there are 33 oxygen atoms, and that obviously is going to be incorrect, whereas this should be the correct answer. What I'd like you to do now is I'd like you to please answer the following questions for your revision. So answer these questions over here as well as this question. This is the end of today's video. Thank you guys for watching. I'll see you guys again in the next video. Bye.